Dear students, I welcome you for the today's lecture related to the understanding of effectiveness NTU method. Now, in general, there are two ways for designing the heat exchanger. That is, to select a heat exchanger that will achieve a specified temperature change in a fluid stream of known mass flow rates. That means you are knowing the mass flow rates and you are knowing the temperatures. This is the log mean temperature difference method. That is the flow rate of the two fluids and their inlet and outlet temperatures are specified. Then you can able to calculate the heat transfer area, so that after calculation of the heat transfer area you can well design the heat exchanger by considering the exchanger layout, the individual heat transfer coefficients, overall heat transfer coefficient, and the pressure drop, and finally the optimization method. Now this is the second method to predict the outlet temperature of hot and cold fluid streams in a specified heat exchanger. That means the heat exchanger is defined. We are having the heat exchanger, and this is the effectiveness NTU method. That means for given heat exchanger, when the flow rates of two fluid and their inlet temperatures are specified, flow rate and only the inlet temperatures are specified, the outlet temperatures are not specified, and is required for this effectiveness NTU method. So this kind of problem encountered in heat exchanger analysis is the determination of heat transfer rate and the outlet temperatures. So not only outlet temperatures, we are also determining the heat transfer rate for the specified fluid flow rates and the inlet temperatures. Now, in analysis of the heat exchanger, we are having the co-current as well as the counter current flow. So we can write the rate of heat transfer in the heat exchanger, that is Q, which is equal to mCp delta T for the cold fluid and mCp delta T for the hot fluid. So this mCp delta T for the cold fluid and mCp delta T for the hot fluid, that is Tc out minus Tc in. Then Mc and Mh are the mass flow rate, that is kgs per second. Cpc and Cph are the specific heats. Th out and Tc out are the outlet temperatures for the cold and hot fluid, and Tc in and Th in are the inlet temperatures for the hot and cold fluid. Now the heat capacity rate, this is the new terminology that is required to understand this effectiveness NTU method. That is the heat capacity rate. The CH, this is the capital CH, remember that this is the capital CH. So this is capital CH is equal to mass flow rate into the heat capacity. Mass flow rate into the heat capacity, and this is called the heat capacity rate. Mass flow rate, that is the kgs per second, and the heat capacity, that makes you the heat capacity rate. So Cc is the heat capacity rate for the cold fluid, that is equal to the Mc into Cpc. So these two equations I can write like this by using this Cc and Ch. This is capital C and capital Ch and capital Cc. Then further we can write the change. Consider the heat exchanger in which the parallel flow is flowing. The derivation which are discussing is related to the parallel flow heat exchanger. So this is a parallel flow heat exchanger, a temperature profile diagram that is shown in the figure, where Th in and Tc in is the temperature gradient on the one end, and Tc to delta T2, which is equal to the Th out minus Tc out on the another end. Now here we have to consider a small infinitesimal area of the heat exchanger, so that the changes taking place in this infinitesimal area, that is the change dTh and dTc, is the small change which will be noted in this area dA. DAS is the surface area for the heat exchanger. In this, the heat that is transferring as D delta Q, which is equal to U delta T into the A. So U into the DAS small area into the change in the temperature difference. This temperature gradient delta T. Now here one assumption is that this temperature gradient that remains constant in this small area. Besides that, the overall uniform, there are certain assumptions. The overall uniform overall heat transfer coefficient is uniform throughout the heat exchanger. Then potential energy and kinetic energy changes are negligible in this small infinitesimal area. The mass flow rates of the fluid are constant. They are not going to change. Then the heat exchange takes place only between the two fluids. Heat losses are negligible, are not accounted. So whatever the heat given by the hot fluid, the same amount of the heat will be absorbed by the cold fluid. That is what the heat exchange takes place only between the two fluids. Then the temperature of both the fluids are constant over a given cross section. This cross section DAS, there the temperature difference is supposed to be the constant, that is delta T. Then heat losses to the surrounding are negligible, then flow conditions are steady and no phase change takes place in the fluid. This is no phase change that is taking place in the fluid. So these are the different assumptions while considering or discussing this derivation. Now delta Q, which is equal to the mHCpH into dTh. Similarly mCCpC dTc. Then in terms of the heat capacity rates also, I can write here capital CH into the dTh, and capital, this can be replaced with the capital C and suffix C into the dTc when I am writing in terms of the heat transfer rates. Now this is the dTh, which is equal to minus dq upon mscph, and dtc, which is dq upon mccpc. So this minus this, that is going to give you dth minus dtc into bracket differential of temperature difference, which is equal to dq, that has been taken out as the common, and 1 upon mch cph plus 1 upon mc cpc, that is taken into account. This is 1 and this is 2, 1 minus 2. And the second equation, that is u delta h delta t into das, the same equation that is taken into account. So here the differential of temperature Th minus Tc, which is equals to the this Q and this Q, they have been equated. So these equations, they are equated and you will get this simplified equation by taking the ln. So the differential term will go out, and this is ln of Th out minus Tc out upon Th in minus Tc in, which is equal to the U overall heat transfer coefficient, surface area for the heat exchange, 1 upon ms Cph plus 1 upon mc Cpc. So this equation is important. The next is the effectiveness. Actually, what it means. The heat transfer effectiveness, it is defined as the actual heat transfer rate upon maximum possible heat transfer rate. This is actually what is happening, how much amount of the heat that is transferred, or and the maximum possible heat transfer rate. For maximum possible heat transfer rate, the temperature difference delta T that can be considered, which is the maximum temperature gradient that can be taken into account, is the Th in minus Tc in. Th in minus Tc in. So this is the maximum delta T temperature gradient that can be achieved, and that is why this is maximum possible heat transfer rate. And this Q, which is equal to the capital C, we have written this in terms of the heat capacity rates. This is Cc and this is Ch into the temperature gradient, where Cc are the Mc and Cp C. So I can write Q maximum, which is equal to the C minimum into the maximum temperature gradient. This is the maximum heat which can be exchanged, maximum possible heat transfer rate that can be achieved. So C minimum, that means either Cc or Ch. C minimum can be either Cc or can be Ch. So either of the two will be taken here as my C minimum, and the multiplied by the maximum temperature gradient that can be accounted, which is Th in minus Tc in. This is the maximum possible temperature gradient. If you take into account the parallel flow heat exchanger, this is the maximum temperature gradient which can be taken into the account on this side, that is Th in minus Tc in. So this is the maximum possible heat transfer rate, where C minimum is the smallest of Ch and Cc, either of the two, whatever the minimum that is there. Now the actual heat transfer rate, that will be the Q dot, which is equal to the epsilon into Q maximum. We have already calculated the Q maximum, which is equal to C minimum into the maximum temperature gradient. So C minimum into the maximum temperature gradient, that is Th in minus Tc in, into the epsilon, that will be the actual heat transfer rate. Then there are two conditions. If Cc is minimum and the second is Ch, that is minimum. So I can substitute both the things and can write the equation epsilon, which is equal to Q upon Q maximum, which is equal to the Cc. Now in this case C minimum, Cc is the C minimum, so C minimum into the Tc out minus Tc in. C minimum, that is Cc, which is equal to Tc out minus Tc in, Cc into the Tc out minus Tc in upon Cc minimum into this thing THI. This can be written here. And the actual heat transfer, that is nothing but Cc, considering the cold fluid, and the temperature difference on the cold fluid, delta Tc. So delta Tc is nothing but Tc out minus Tc in. Similarly, for Ch is equal to the C minimum. This is Ch equals to the C minimum, and this equation that can be written here, that is Th in minus Tc in, Th in minus Tc in. And similarly, the actual heat transfer for the hot fluid, that will be Th in minus Th out. So this can be simplified to this, and here the epsilon values, they are simplified. Now we have already derived this equation, that is ln of Th out minus Tc out upon Th in minus Tc in, which is equal to the UAS into 1 upon Ch, capital Ch, plus 1 upon capital Cc. The same equation I am writing here, that is from the first line of the equation of this PPT. Then from the effectiveness equation, I can write, for this effectiveness equation, I can write here Th out, which is equal to the Th in. That means I am writing Th in minus Th out, which is equal to the, from this equation I can write the corresponding equation, that is Cc upon Ch, which is equal to Tc out minus Tc in. This equation I am substituting it here. This second equation, that will be there. This equation is there. Then substituting the value of Th out from this equation. So it will be substituted as this terminology here. So it will be Th in, and adding and subtracting this Tc in value for this simplification purpose. The rest of the thing is the same equation here. Th in, then this equation that is there, and Tc out, that is directly coming from here. And rest of the equation is same, right hand side that is same, the denominator is same. Now I will write this term, that is Th in minus Tc in, below this two term, that is Th in minus Tc in. So this will get cancelled, and it is this one that will come into the picture. The next is Tc in minus Tc out. Here also Tc out minus Tc in. So I can write here minus of this bracket will be same as this. So I will take out the minus, that is as a common, and here 1, and here it is taken as Cc upon Ch, Cc upon Ch, and the ratio of Tc out minus Tc in upon Th in minus Tc in, that will remain there, and right hand side that is same. Now the epsilon, which is the actual heat transfer upon maximum possible heat transfer for the cold fluid, I can write this equation. So here Tc out minus Tc in upon Th in minus Tc in. So these equations, they are same, and this can be replaced as the epsilon C minimum upon Cc. So this epsilon, after simplification, you will get epsilon for the parallel effectiveness for the parallel flow, that as 1 minus e raised to minus UAS upon Cc into bracket 1 plus Cc upon Ch upon 1 plus Cc upon Ch into C minimum upon Cc. So this is the final derivation, final equation you will get. This is we have discussed related to the parallel flow heat exchanger. Similarly, we can have where the C minimum upon C maximum, that is the C, or in some books the R that is written, and this is called the heat capacity ratio. This is some books it is written as the R, or some books it is written as the C. So this is the capacity ratio, that is the C minimum to the C maximum. And NTU, that is the number of transfer units, which is equals to the UA upon C minimum. From here UA upon C minimum, that will be there as the NTU. So the effectiveness relationship for the heat exchangers typically involves the dimensionless group. One is NTU, that is UAS upon C minimum, and the second is the capacity ratios. For specified values of U and C minimum, the value of NTU is a measure of the surface area AS. Looking at this equation, for these specified values of U and C minimum, that means U for that heat exchanger overall heat transfer coefficient that is known, the value of NTU is a measure of this surface area, heat transfer area. Thus, the larger the NTU, the larger the heat exchanger, and this will depend on U upon MC minimum. So NTU is larger, you will require the higher surface area. The effectiveness of heat exchanger is a function of number of transfer unit NTU and the capacity ratio C. So this effectiveness, which is function of the NTU and the heat capacity rates ratio. As we have discussed it for the parallel flow, one can derive the similar equations for the counter flow heat exchanger. There the equation is slightly modified, that is 1 minus e raised to minus NTU into bracket 1 minus C upon 1 minus C into e raised to minus NTU 1 minus C. Similarly, for shell and tube, one shell pass and 2 4 tube passes, the equation can be derived like this. Then cross flow single pass, then for C maximum mixed and C minimum unmixed, then all these are the different conditions. Now there are the different graphs which are available, which is incorporating the effectiveness epsilon and the number of transfer units for the different values of the C. So here the things are NTU, the C, and the effectiveness. These three numbers, epsilon is there, the NTU is there, and the ratio of heat capacity that is there. So I can plot a graph that is the effectiveness which is equal to the NTU and the C. C is nothing but the C minimum upon C maximum. So the graph behavior is like this, and the ratio of this C minimum to the C maximum, that is the capacity ratio, which can be considered as the 0, then 0.25, 0.5, 0.75 and 1. All these are the different C ratio values. So for a particular effectiveness and for the NTU values with the different ratio of the capacities, I will be able to calculate the temperatures for the outlet fluids for the hot and cold material. Now this is for the parallel flow. This graph is for the counter flow heat exchanger. This is one shell pass 246 tube passes, two shell passes 2468 tube passes. So that will depend on the number of shell passes and the number of tube passes. So these graphs, they are of more importance. Then the different cases. The case of a condensation and the case of a boiling, where in the case of a condensation and boiling, the temperature of the hot fluid in case of a condensation, that is the constant. Only the latent heat lambda that is getting transferred, so the temperature of the condensing fluid, that remains constant. And in case of a boiling process, only the latent heat is absorbed, so the temperature is constant. However, the phase change from liquid phase to gaseous phase is there. Only the latent heat that is transferred, no sensible heat that is gained. So in that cases, the condenser CH tends to infinity, and in case of boiler CC, that tends to infinity. That is what we will talk, where R that is equal to the 0 are the heat capacity rates, R or C, that is the C minimum upon the C maximum. This is applicable for the condensation and evaporation or the boiling processes, where one fluid remains at a constant temperature through the exchanger. So this effectiveness equation that reduces to 1 minus e raised to minus NTU. So this equation of parallel flow heat exchanger, that reduces to 1 minus e raised to minus NTU, because C is having the value of 0. So only the effectiveness that comes as 1 minus e raised to minus NTU. So C minimum is infinite, and thus R, which is equals to the 0. No matter how large the exchanger is or how large the overall transfer coefficient is, the maximum effectiveness for the parallel flow heat exchanger is around 50%, and for the counter flow it can attain up to the 100%. So counter flow, that is usually more advantageous for all operations. And there can be the case too, that is for the regenerators, where R, which is equal to the 1. This parallel flow heat exchanger using the R, which is equal to the 1, the effectiveness equation that becomes or reduces to 1 minus e raised to minus 2 times NTU upon 2. So this NTU is a measure of heat transfer size of the exchanger. The values of NTU, the closer the heat exchanger approaches its thermodynamic limits. So this is all related to the effectiveness method, in which we are calculating the heat transfer coefficient and the outlet temperatures.